Alrighty, I think I'd like to try to illustrate with some Oreo cookies what a buffer solution is. That's kind of hard to see all these Oreo cookies go to waste, but it's for a good cause. Alright, so what I want you to do to kind of catch the picture here is imagine an Erlenmeyer flask, a very big one, containing 1 liter of a solution. Not just pure water, but in that I want to have 1 mole of what we're going to call the bicarbonate ion. If you look at that, what it has in it, we'll say is 1 proton on the outside here that is not, I guess, met with another proton on the other side. So we'll say this is a bicarbonate. So I'm going to write that in right above that. And we're going to say this pile represents, again, 1 mole of bicarbonate. And what you have to do is buy it, of course, as a salt. So we'll say NaHCO3. So that's our 1 mole of sodium bicarbonate. Now on the other side, this was a little bit harder to make, and it's very gooey. That makes these so good. Maybe you'll remember this, I guess. I will. So we have 2 sites that were without protons. So we have this site here and this side here that don't have the cookie. We have the cream. So what this is going to be, if I can write this, it'll be sodium carbonate. So we have, again, 1 mole. And I've kind of not made it perfect here, so the carbonate's falling apart. There should be 10 of these pieces here. We'll just imagine there are 10 here. I'm going to put this broken one to the side. You just stay put as a representative. So we'll imagine 10, and they're going to represent like 0.1 mole each. So each one of these represents 0.1 mole of carbonate, and each one of these over here represents a 0.1 mole. So if we had 10 and 10, 0.1 times 10 would be 1 mole, and 0.1 times 10 would be 1 mole. So we'll say we put those two together, fill up the Erlenmeyer flask up to 1 liter, and we would have 1 mole of NaHCO3, sodium bicarbonate, in a liter, and we'd have 1 mole of sodium carbonate in a liter. So again, 1 mole of each. So we'd have, if you remember molarity from previous discussions, we'd have 1 mole per liter of both. All right, so let's get to the exciting part. So that's kind of what you do to make a buffer. You have some sort of what we'll call weak acid, and sodium bicarbonate has this proton that it can give up. It's a weak acid. It's also a weak base, so it actually can be used by itself to make a buffer. But to illustrate kind of a buffer, we're going to say 2 different species. A weak acid, again, can you guess what this one will be? If this one's the weak acid, well, we're going to make this, or use, a weak base. So that's basically what you have to have a buffer. You have to have some sort of weak base and high concentration of it, and you have to have a weak acid and a high concentration of it. And why high concentration? So whatever you add in to your solution, it can absorb the shock, so to speak. Sorry for the bell. It can absorb the shock. So what we're going to imagine is these are protons, no cream, and they each represent 0.1 mole. So what I'm going to do is I'm going to add a 0.2 molar strong acid so it fully dissociates to make these protons. I'm going to add that to the water. So they're going to come into the water. And what would happen? These are strong acid protons. Well, they're going to react with the weak acid, or are those 2 strong acids going to react with the weak base? I hope you're saying the weak base. So what we'll do, so instead of having a 1-to-1 ratio, 1 mole to 1 mole, now I'm going to have these react with the weak base. I'm going to put this together. Please stay together. I'm going to push that together a little bit, and we now just made a bicarbonate. So if I take that and compare it to what I already have, they're exactly the same, minus this little imperfection here. So that's going to join the bicarbonate side, or the sodium bicarbonate, minus this Na. But typically when you add, I guess, strong acids, you're going to have some counter ions. So let's go ahead and add this now proton, strong acidic proton gets bound by the weak base, and we now have a another bicarbonate. So I've put it in the bottle. Now if you notice, we would have, if we had a 10 to 10, it's now going to be a 12 to 8. Or we would say a 1.2 mole to 0.8. Now if you've noticed, what we've done then is what we had initially was a 1-to-1 ratio. And now we have a 1.2 to 8 ratio. It hasn't changed much. So we've kept those acids that come in from controlling the pH of the water. You say, well, wait, aren't these somewhat acidic, the weak acid? It's so small that we really don't see much of a high concentrate. We don't see much of those protons made from the weak acid. That's why we use it. It's so that anything that comes in gets absorbed by taking one of those weak bases with it. Now we can go the other way and have a strong base come in and start making more of the carbonate from the weak acid. But this video, I don't want it to be too long. It's already about 6 minutes long. We're just showing how strong acids can come in and be absorbed. Now remember, when we first make this solution of buffer, we don't really worry about too much of the pH changing because the weak acid is added. In other words, we don't see much of that proton being given to the water because it's a weak acid, 10 to the minus 10 or 7. It doesn't give much. And this doesn't take and grab a lot of the protons from water to make a lot of hydroxide because it's a weak base. So you pretty much have what you've added to water unchanged. This goes in and stays put, and this goes in and stays put, ready to react with any weak, strong acid that comes in or strong base. Thank you. Bye-bye.